The goal of a baseball team is to make the playoffs. The A's approach was to get to the playoffs by using analytics. We'll first show how we can predict whether or not a team will make the playoffs by knowing how many games they won in the regular season. We'll then use linear regression to predict how many games a team will win using the difference between runs scored and runs allowed, or opponent runs. We'll then use linear regression again to predict the number of runs a team will score using batting statistics, and the number of runs a team will allow using fielding and pitching statistics. We'll start by figuring out how many games a team needs to win to make the playoffs, and then how many more runs a team needs to score than their opponent to win that many games. So our first question is, how many games does a team need to win in the regular season to make it to the playoffs? In Moneyball, Paul DePodesta reduced the regular season to a math problem. He judged that it would take 95 wins for the A's to make it to the playoffs. Let's see if we can verify this using data. This graph uses data from all teams and seasons from 1996 to 2001. There's a point on the graph for every team and season pair. They're sorted on the x-axis by number of wins and on the y-axis by team. The gray points correspond to the teams that did not make the playoffs, and the red points correspond to the teams that did make the playoffs. This graph shows us that historically, if a team won 95 or more games, or is on the right side of this line, then they almost all made it to the playoffs. But if a team only won, say, 85 or more games, then they were likely to make it to the playoffs, but it wasn't as certain. And if a team won, say, 100 or more games, then they definitely made it to the playoffs. So this plot shows us that historically, if a team won 95 or more games, then they had a strong chance of making it to the playoffs, which confirms Paul DePodesta's claim. So we know that a team wants to win 95 or more games. But how does a team win games? Well, they score more runs than their opponent does. We just need to figure out how many more. The A's calculated that they needed to score 135 more runs than they allowed during the regular season to expect to win 95 games. Let's see if we can verify this using linear regression in R. In our R console, let's start by loading our data. We'll call our data frame baseball and use the read.csv function to read in the data file baseball.csv. Don't forget to make sure you're in the folder on your computer containing this file first. We can look at the structure of our data using the str function. This data set includes an observation for every team and year pair from 1962 to 2012 for all seasons with 162 games. We have 15 variables in our data set, including runs scored, RS, runs allowed, RA, and wins, W. We also have several other variables that we'll use when building models later on in the lecture. Since we're confirming the claims made in Moneyball, we want to build models using data Paul DePodesta had in 2002. So let's start by subsetting our data to only include the years before 2002. We'll call our new data frame Moneyball, and we'll use the subset function to take a subset of baseball and only take the observations for which year is less than 2002. If we take a look at the structure of Moneyball, we can see that we now have 902 observations of the same 15 variables. So we want to build a linear regression equation to predict wins using the difference between runs scored and runs allowed. To make this a little easier, let's start by creating a new variable. We'll call it Moneyball $RD for run difference and set it equal to Moneyball $RS runs scored minus Moneyball $RA runs allowed. If we take a look at the structure of Moneyball again, we can now see that we have a new variable, RD, at the bottom of our variable list. Now before we build the linear regression equation, let's visually check to see if there's a linear relationship between run difference and wins. We'll do that by creating a scatter plot with the plot function. On the x-axis, we'll put RD, run difference, and on the y-axis, we'll put W, wins. This scatter plot shows us that there's a very strong linear relationship between these two variables, which is a good sign for our linear regression equation. So now let's go back to our R console, and we'll create our linear regression model, which we'll call wins, REG, and we'll use the LM function to predict W, or wins, using the independent variable RD. And we'll use the data set Moneyball. We can take a look at the summary of our regression equation using the summary function, which shows us that RD is very significant with 3 stars, and the R squared of our model is 0.88. So we have a strong model to predict wins using the difference between runs scored and runs allowed. Now, let's see if we can use this model to confirm the claim made in Moneyball that a team needs to score at least 135 more runs than they allow to win at least 95 games. Our coefficients table tells us that our regression equation is wins equals the intercept term 80.8814 plus the coefficient for run difference 0.1058 times RD, or run difference. We want wins to be greater than or equal to 95 so that the A's make it to the playoffs. This will be true if and only if our regression equation is greater than or equal to 95. So we want 80.8814 plus 0.1058 times run difference, or RD, to be greater than or equal to 95. By rearranging this equation, we can see that this will be true if and only if run difference is greater than or equal to 95 minus the intercept term 80.8814 divided by 0.1058, the coefficient for run difference. This is equal to 133.4. So this tells us that if the run difference of a team is greater than or equal to 133.4, then we predict that the team will win at least 95 games. This is very close to the claim made in Moneyball that a team needs to score at least 135 more runs than they allow to win at least 95 games. So by using linear regression and data, we were able to verify Paul de Podesta's claim.